Good evening. My name is Adarsh Pal Singh, and I'll be presenting my paper titled Embedded Machine Learning Based Data Reduction in Application Specific Constrained IoT Networks. So, I'm a final year Bachelor's and MS by Research dual degree student at IIIT Hyderabad, India, and I've authored this paper with my research advisor, Dr. Sachin Chaudhary. So, let's start with the basics of what we have done, why we have done it, and what are our contributions to the problem statement. So in a nutshell, this is a data transmission reduction scheme that uses machine learning to reduce the number of data transmissions from constrained wireless sensor nodes to the edge for application specific IoT networks. So this is the gist of it. Let's take a look at why data transmission reduction is important to Internet of Things. We know that numerous IoT applications require wireless sensor networks to be deployed in regions where wired power supply may not be available to these sensor nodes. So consequently, these sensor nodes are battery powered and they typically follow a sleeping pattern wherein they will wake up every so often to sense the data, transmit it, and then again go back to sleep. And it is known that radio transmission is the biggest culprit when it comes to energy consumption. So these points bring us to a very important area of research, that is to increase the lifetime of such sensor nodes by decreasing the amount of data transmissions without compromising much on the data quality. So let's take a look at what all has been done till now. There have been quite a few papers on low complexity data compression techniques that can run on the microcontrollers to shorten the data packets. But the problem with these are that whenever the sensor nodes wake up, they still have to transmit these short packets. So the transmission periodicity remains the same. That's why when it comes to data transmission reduction, the more popular approach is of dual prediction models. In this, the trained model runs on the sensor node and the same model runs on the edge. And the sensor node initiates transmission only when the predicted value exceeds the newly sensed value by some predefined threshold. These can be broadly classified into two types. First are filter-based techniques. In this we have dual Kalman filter and the least mean square filter. So LMS is actually more popular than Kalman because it is more flexible and has a lower computational complexity cost. In time series we have linear regression, moving average, exponential weighted moving average, Harima and Shewhart. So I have italicized Shewhart because it has been proven to be more optimal than LMS and the other time series techniques when it comes to the number of transmissions and the root mean square error metric on the data collected. Coming to what we are trying to achieve with our technique is when it comes to application specific IoT networks, the techniques that I've listed here are not intelligent enough to take data importance or the application into account when they decide to initiate transmission or not to, because these are simple thresholding based techniques which use a predefined threshold. So for application specific IoT networks, this is something that we have tried to do. We have tried to take the application into account to ensure that we have minimum transmissions from the sensor node to the edge. So let's briefly take a look at the Shewhart algorithm because we have used it in comparison with our own technique. So for simplicity, consider a sensor node with a single sensor. The first thing we do is we define an error threshold for this sensor. So when this node senses a new sensor value, let's call it x of t, we basically check if this new sensor value and the previously transmitted sensor value exceeds this error threshold or not. And if it does, we transmit it. Otherwise, we simply discard this new sensor value. So if we have multiple sensors attached to this node, we'll basically have multiple error thresholds, one for each sensor. So consequently, the edge follows a simple rule. In a particular time interval, if it receives a sensor value from the sensor node, it takes that value. Otherwise, it will take whatever was previously received by the edge from the sensor node to be true for this interval as well. So our contributions are threefold. First, we have introduced a new embedded machine learning based data transmission reduction scheme for application specific IoT networks. Second, we provide an in-depth analysis, both practical and theoretical, of 5 supervised machine learning algorithms in the context of constrained microcontrollers. And third, we provide an insight into how our scheme can be adapted to an actual IoT setup of occupancy estimation. So before moving on to our data reduction scheme, let's answer a very crucial question first. Can microcontrollers actually run machine learning algorithms? And the answer is both yes and no. So when it comes to training, we know that the datasets these days can range anywhere between hundreds of megabytes to several gigabytes. So huge amount of memory is required. And solving the training optimizations on these datasets again requires huge amount of computing resources, far greater than what a typical microcontroller can provide. So training is completely out of the question. But many of these algorithms actually boil down to simple parameters that require standard arithmetic and logical operations when it comes to testing or inference. And these can be done on the microcontrollers. In particular, we'll be taking a look at these 5 algorithms in the context of microcontrollers. So the answer to the original question is yes, it can be done if you train the machine learning model elsewhere and then offload the trained parameters to the microcontroller. It is possible to run the inference in real time for some algorithms. So let's start with linear discriminant analysis. LDA assumes that the class conditional distribution of data, which is this probability where x are your data points and y is your classes, as a multivariate Gaussian shown by this equation right here. The predictions are made using Bayes' rule. So during training, your covariance matrix, your means vector, and your priors are basically learned by the algorithm. And if you solve these two equations for binary classification, the inference boils down to a simple equation, which is x transpose w greater than less than c. So c is this big formulation, which when solved boils down to a single 4-byte floating point constant, and w is a d cross 1 floating point vector. So both c and w can be calculated at the edge and then offloaded to the microcontroller. So looking at this, you can clearly see that you have d amount of multiplications, where d is your dimension of the data and the dimension of your vector as well. So you have d amount of multiplications and d minus 1 additions and a single comparison when it comes to inference. QDA is very similar to LDA. The only difference is that the covariance matrix K is now calculated for each of the classes separately. And that's why when it comes to inference, you have this another term apart from x transpose W. And because of this, the multiplications and the addition subtractions are off the charts as compared to LDA. Gaussian naive Bayes, as the name suggests, is based on the Bayes theorem, which assumes that all the D features of the dataset given the class label are mutually independent. That's why when you look at the classifier formulation right here, you see that everything here is in multiplications because of this independent property. So solving this and simplifying for binary classification, the inference boils down to this equation, where C is again a big formulation, but it simply boils down to a simple 4-byte floating point constant, and then you have two D length arrays. So these three, along with mu0s and mu1 arrays, have to be offloaded to the microcontroller for inference. And when it comes to complexity, there are 4D multiplications and 4D minus 1 additions involved. SVM is a very popular linear classifier. In a D-dimensional space, SVM simply tries to find an optimal hyperplane that can separate the two classes. So when it comes to inference, you basically have to check in which half of the hyperplane the new point lies in. So this can basically be done by W transpose X greater than less than B, where B is the intercept of your hyperplane. So this is a 4-byte floating point constant, and W is the weight vectors corresponding to the hyperplane equation. So this is a D cross 1 floating point weight vector. The X is not the raw value. Basically, since the algorithm is scale variant, you have to make all your data points to have mean 0 and variance 1. After that, if you see this formulation and the standard scaling formulation, you will basically be left with 2D multiplications and 2D minus 1 addition and subtractions for inference. So decision tree is again a very popular supervised machine learning classifier. So it basically learns optimum decision rules from the training set and then discriminates between different classes based on these rules. So if you see this diagram, decision tree basically pans out to be a if-else ladder, where each of the branch is basically a logical test and the leaves are one of the labels, class labels. So each root to leaf path is basically something like an if condition, and then finally label that you get down to. So all of these root to leaf paths have to be converted to if-else statements and then offloaded to the microcontroller. Memory complexity wise, it basically depends on the average depth of the tree and the number of leaves node that you have. So this will be considering that each number can be a floating point. We have 4D average into n leaf as the memory complexity, and the time complexity of this algorithm would be on average the number of logical operations that we do for inference and the complexity of these logical operations. So this table represents the complexities of different machine learning algorithms that we have discussed so far. So among these four, LDA is clearly the least computationally expensive and the lightweight algorithm. SVM comes in a close second. So SVM and LDA have a very similar inference formulation, but because the data points need to be scaled in case of SVM, this adds up to its complexities. QDA is clearly the most computationally expensive and the most memory requirement based algorithm that we have discussed. Coming to the practical part, we had done some experimentation of ATmega 328 with data sets of different dimensionality. So you can see dimensionality being represented in the x-axis and the execution times of each of these data sets for the inference of each of these data sets. We see that this graph agrees with what we have discussed in the theoretical part. You see the LDA in the bottom part of this chart. Then SVM comes in a close second. And the quadratic dependence on the data dimension is clearly visible in case of QDA. One thing to notice is that the inference for QDA does not exist for data dimension greater than 17 because the ATmega 328 runs out of memory beyond that. So this is something that one needs to keep in mind if one wants to use QDA for higher data dimensions. So let's take a look at our proposed data reduction scheme now. We assume that the sensor nodes follow a typical sleeping cycle wherein the sensor nodes would wake up every so often to sense the data points, decide whether to transmit or not, and then go back to sleep again. Since this is a machine learning based scheme, the first thing to do is to acquire a training data set and train one of the 5 algorithms that we have discussed either at the edge or the cloud. And once that is done, you simply offload the trained machine learning model parameters as we have discussed before to the sensor node. The sensor node would wake up every so often, measure the new sensor values, and since the machine learning model is present here itself, we can estimate the class label Y here itself. And this is the data reduction part now. We basically check if this new class label is different from the previously transmitted class label. So this is another way of saying, has the application changed? And if it has, then we transmit it to the edge device because the edge needs to know about it. Otherwise, we simply go back to sleep. So this is the data reduction scheme that we have come up with. So to validate our proposed data reduction scheme, we chose an IoT application of occupancy estimation. Let's take a look at the experimental setup for that. So each of our sensor node has an Atmel ATmega 328P, which is battery powered. It is connected to 3 different sensor nodes: temperature, humidity, and light. You can see their specifications in this table. And each of them has an XB/X2C for communicating the data values. Consequently, the edge also has an XB/X2C to collect these data values and then report it to the Raspberry Pi 3, which is powered by the mains. The experimental setup had 4 different sensor nodes deployed in a star configuration, each of them connected to the edge via the XB/X2C. The sensor nodes were programmed to transmit data every 30 seconds. Since our scheme is based on machine learning, we basically needed the data set, and this is how we collected the data set. The edge basically timestamped every data point it received from the sensor nodes, and the occupancy ground truth in the room was recorded manually. You can see that the room is divided into 4 zones. This was not a physical division. This is a virtual division. We'll see why this is important. In each of the zone, the occupancy can be either 0 or 1. But in the entire room, it ranged from 0 to 3. This is a slice of the data set. You can see how different environmental parameters correlate to occupancy. You can see the occupancy count here and corresponding correlations to humidity, light, and temperature values. So it is this property that makes occupancy estimation possible using environmental parameters. So this has actually been studied a lot in literature. So now that we have seen our data transmission reduction scheme and the occupancy estimation test bed, let's take a look at the intersection of the two. So with the collected data set, 3 different experiments were simulated on it. In the first one, no data reduction was done by the sensor nodes. In the second one, the sensor nodes ran a Shewhart-based data reduction scheme. And in the third experiment, the machine learning-based data reduction scheme was employed. So let's take a look at these 3 experiments in detail. So in the first experiment, no data reduction was employed. So the sensor nodes basically transmitted data periodically to the edge without any data reduction scheme, and the edge was responsible for the inference. So since machine learning is being run on the edge, there is no bound for the complexity of algorithms that can be run. That's why apart from the 5 machine learning algorithms that we have discussed, SVM with RBF kernel and random forest was also used. So to basically simulate this experiment, we did a 10-fold stratified cross-validation on the complete data set to get the accuracy and the F1 score metrics. So in the second experiment, the sensor nodes basically use Shewhart data reduction scheme, and based on that they send data to the edge. So recall that in Shewhart, each sensor basically has an error threshold attached to it, and not just for Shewhart but for other prediction schemes as well. The thresholds are derived from sensor accuracy, resolution, and mean of the data. And based on these parameters and the data set, we basically arrive with 4 different scenarios for different thresholds. ET is for temperature threshold, humidity, and error threshold for light. So basically have 4 different scenarios. And to simulate this experiment, we did a 10-fold stratified cross-validation on the complete data set. And in each iteration of this cross-validation, we basically simulated Shewhart. And that's how we were able to calculate the accuracy F1 score and the number of transmissions that were sent. So this brings us to the experiment on our own data reduction scheme. The sensor nodes run our own machine learning based data transmission reduction scheme with the edge just maintaining the occupancy count of each zone. The machine learning model of each sensor node was basically trained on the data of that sensor node and the corresponding zonal occupancy count. To simulate this entire experiment, we basically did a 10-fold stratified cross-validation on each of the individual sensor node data sets. And based on the predictions we got, we were able to calculate the number of transmissions based on the number of changes in the class labels that happened. And these zonal predictions were summed up to get the occupancy count of the entire room. This gave us the accuracy and the F1 metrics for the occupancy estimation of the entire room. And so this is basically a distributed detection problem because each sensor node is running an independent machine learning model and not sharing data with others. So let's take a look at the results of our experiments now, starting with the accuracy and F1 metrics of different experiments and the machine learning models. The first thing to notice is that LDA outperforms linear SVM for almost all cases, even though LDA and SVM have a very similar inference formulation and they're both linear classifiers. So this does suggest that the Gaussian assumption holds well for LDA. Random forest outperforms decision tree for all the experiments. This is also expected because of the ensemble nature of random forest. This is basically a collection of different decision trees. GNB performs the worst. This implies that the feature independence assumption doesn't hold well. And if you recall the dataset slides that we had seen, in which we could see that the different features were correlated when juxtaposed with the occupancy count, this does make sense. The best result is given by our SVM with RBF kernel on the complete data set. And for our distributed detection experiment, we get the best result with linear SVM, and this is comparable to the best of the others. So this plot is basically the highlight of our result section. On the x-axis, you have the sensor nodes, and on the y-axis, you have the number of transmissions. The bars in the brown orangish hues belong to the Shewhart based data reduction schemes, and the colorful bars are for the machine learning based schemes. Clearly, you can see that all the 5 machine learning based algorithms outperform Shewhart based data reduction schemes for each sensor node by a huge margin. Sensor node 3 was kept near the window, so it faced the most variation in the light data, and clearly Shewhart based schemes seem to be affected by fast changing variations. Linear SVM gives the least amount of transmissions, which are 10, 11, and 9 out of 10,153 points respectively, which is a huge reduction in the number of transmissions. Now it may seem as if we can downsample the Shewhart dataset more to match the number of transmissions of linear SVM by increasing the error thresholds for the sensors. And we showed this in the paper also, that using trial and error, we were able to get the thresholds which gave us the number of transmissions as 10, which the linear SVM gives. But the performance took a big hit because the F1 score with SVM with RBF kernel was around 0.61, which is a huge downgrade from 0.916, which the linear SVM gives for the same amount of transmissions. So in general, we can say that the machine learning based schemes show 18 to 82 times reduction in the number of transmissions as compared to Shewhart, and 99.91% reduction overall in the best case while imparting similar performance. So this brings us to the conclusion of our work. In this work, we described offloading strategies for 5 machine learning algorithms to constrain microcontroller devices. And based on this, we proposed a new machine learning based data transmission reduction scheme for application specific IoT networks. We gave an insight of how the scheme can be adapted to occupancy estimation IoT application. For the occupancy estimation application, it was shown that the machine learning based data reduction schemes outperform Shewhart based schemes by reducing the number of transmissions by 18 to 82 times while imparting similar performance. And overall, 99.91% reduction in data transmissions was achieved in the best case of linear SVM. So in the future, we plan to adapt our machine learning based data transmission reduction scheme for more IoT applications, and also add more supervised and unsupervised learning algorithms under the umbrella of constrained devices. So this scheme was actually for constrained devices, but for resource abundant devices like smartwatches and smart vehicles, more complex machine learning models can be used to intelligently prioritize data transmissions. Not everything that the device has to be told to the edge, but the device also does not have to do everything on its own. So that is the whole point. So this brings me to the end of my presentation. For any queries, please feel free to email me or Dr. Sachin. We are also open to having a discussion via Skype or Zoom. Thank you very much.